Hi, my name is Juan Suarez, and this is Video Lab 5. In this lab, our objective is to explore the dynamics of a spring mass system undergoing oscillatory motion in 2 dimensions. This analytical approach will allow us to understand the spring mass system and how it uses the floor and the spring to bounce back up, and it explains terms like momentum within these fundamental physical phenomena. Within the scope of this lab, Newton's second law will still apply, because the net force will also include the force of the spring and the force of gravity that is acting on the object. When referring to the energy principles, which include the conservation of energy within an isolated system, we can talk about the kinetic energy, we can talk about potential energy, specifically gravitational potential energy, and spring potential energy. Momentum in the scope of this lab represents a quantity of motion that is possessed by an object, which is calculated by the mass and the velocity and is used to understand collisions and other sorts of phenomenons and interactions. And we can see this in the lab by the spring and how it bounces. The questions that will be asked for this experiment are the experimental versus the computational, the relationship between the energies, how will the graphs look like, and does the code give evidence to the experiment? Specifically, the experimental versus the computational. This lab, for the most part, is purely experimental, but when we computate the data and try and find a graph for it, we're going to see that these graphs are going to look exactly the same. It's going to start at a position 0, and then since it will be dropped, then obviously the position of the slinky will go down. And then the relationship between the energies, we know that as kinetic energy increases, potential energy decreases. So there's going to be that relationship that is inversely proportional between the two. And these graphs, how it's said at the start, are going to be a decline once it drops. And then the coding does give credit to the experiment because of this that I've stated before. The system and surroundings of this lab are, the system is the spring mass system, and the surroundings is the air resistance, the gravity, and the external factors. The only constants that we will know for this lab include the ball mass, which is 0.25, and that the velocity and the position will start at 0. To replicate this experiment, you would just need a spring and the tracker/recording device. To replicate the experiment, we would first need to obtain the video file for analysis, which can be found in Canva. We can use the track software to analyze the motion of the mass, where then we can extract the position data, and then this position data we can copy into an Excel spreadsheet to find a graph and connect it with the code. When we extract the video from the tracker, and we can see that the slinky is going to go down, and then it's going to bounce up, because it is a spring, so a spring, once it is compressed, it will release energy that will then shoot it upwards. And we can see here in the Y section of the tracker that the position does go down as it does fall due to gravity. And this can also explain the changes in energy, including from kinetic energy, which changes to potential energy, and some of that potential energy can also be changed into spring potential energy. So the way that we calibrate this is that we put the center of mass at the slinky, and then we track the slinky at each frame. And when we look at the code and understand what the code is trying to decipher, we first talk about it in the terms of work, and we talk about it in the terms of force and time. The time that we got was taken from the tracker, and the most general things we can see here, we have the velocity of the ball, we have the normal kinematic equations, we have momentum principles, we have Newton's second law. And using this, we can calculate that position that the spring has. And when we combine both the data that we got from the tracker and the data that we got from the code, we can see that obviously the model that we got is going to be perfect, because a code will run exactly as if it was elastic and no errors, while the experimental data still has the same trajectory, but obviously due to frame spikes and all little intricacies, there's going to be a bit of bumps in the way, but for the most part, it does show the same trend. For this lab, the only big sources of error we can find are the simplification of formulas, as we will never have a specific finite number, and therefore the formulas will be a generalization of what it could be, and then air resistance will always play a factor, because this will make it seem like it is an inelastic collision and it is not perfectly elastic. What does it mean if we increase the spring constant in the spring mass system? By increasing the spring constant and making it stiffer, it will require more force to stretch or compress, which can make the system be more inelastic, because it will require more force for it to be compressed and come back to its original height. What if we increase the mass of the object attached to the spring in the system? By increasing the mass, it would result in a decrease in the collision, making it slightly more inelastic or elastic, depending on what you do, because it would require a larger mass that would force more acceleration and deceleration. And by adding more mass in a spring mass system, it wouldn't change the kinetic or the potential energy, but it could have an effect on the spring potential energy. In conclusion, our experiment delved into the dynamics of a spring mass system in 2 dimensions, employing video analysis and computational modeling. This approach allowed us to understand more about the spring mass systems and how energies can relate to each other and how elastic and inelastic collisions work in terms of springs.